Welcome back. In today's video, we are going to discuss neutralization of acids and bases and something called titrations. So first off, let's talk about this neutralization reaction. What does that mean? Well, when an acid and a base are mixed together, the concentrations of your H plus ions and your OH minus ions are affected. Those hydrogen ions and hydroxide ions are going to affect each other. And if you've got an acid, you've got more hydrogen than hydroxide, and a base, more hydroxide than hydrogen. Well, when you mix the two together, they kind of cancel each other out. Those hydrogen ions and those hydroxide ions are going to basically form water. And so you're going to end up with a more neutral pH. It's going to bring your pH closer to 7. If you've got an acid and you add a base, it's going to bring that pH up towards 7. If you have a base and you add an acid, it's going to bring the pH down towards 7 because you're getting closer to having an equal number of hydrogens and hydroxides. So as you mix them together, they're going to bring themselves close to neutral. That is what we call an acid-base neutralization reaction. When they are neutralizing or becoming closer to neutral is a neutralization reaction. So neutralization reaction, by definition, is a reaction in which an aqueous acid and an aqueous base combine to form water and a salt. Now when you hear the word salt, you're thinking of the stuff you sprinkle on your food. But in chemistry, a salt is any ionic compound formed from the anion of an acid and the cation from a base during a neutralization reaction. So salts are actually a classification of compounds. So this is an example of a neutralization reaction. Potassium hydroxide plus nitric acid are going to produce water and potassium nitrate. So in this reaction, you're going to have an acid and a base are producing a water and a salt. So what's what? Well, we have nitric acid is of course the acid. And then we have potassium hydroxide has hydroxide, that is our base. And then of course water is H2O. So what is this last thing? That is our salt. So if you ever wanted to identify what the salt in a neutralization reaction is, you can identify the acid, you can identify the base, and then water is easy, and so whatever's left is the salt. So the definition of a salt is the cation from a base. So you'll notice that potassium nitrate, or salt, has the cation potassium, and that potassium came from the base, potassium hydroxide. And then it has the anion of the acid. So nitrate is the anion of our nitric acid. And so that is what forms together to form our salt. Now basically these are double replacement reactions because they're switching partners, and just one of those products is water. The H and the OH go together and make water. And so you have it's a double replacement reaction, but it is a specific kind of double replacement reaction where you're having an acid and a base neutralizing each other. And that brings us to something called titrations. And this is what we use to analyze acid and base neutralizations. A titration is the process of using a solution of known concentration to determine the concentration of an unknown solution. So let's say we have a concentration of acid. We don't know what its concentration is, but we can make a base that has a known concentration, and then we do a titration to help us figure out what the concentration of that unknown acid is. So to discuss this, let's talk about the different parts. So we're going to titrate a standard solution. A standard solution is the solution of known concentration. It's also called the titrant. It's the one that we're titrating in. Okay? So then we have the analyte solution. The analyte solution is the solution of unknown concentration. It's also sometimes called the titrant. It's the one we're trying to find, or the one we are analyzing, hence the reason it's called the analyte. Right? You're also going to use an indicator. And as we discussed before, we talked about litmus paper. An indicator is a chemical compound whose color changes based on the pH of the solution it's in. There's lots of different indicators. You have bromethymol blue, we have methyl red, we have universal indicator, we have phenolphthalein. All of these indicators are things that change colors at different pHs. So you can use them to find something at certain certain pHs because they all change colors at a different pH. Universal indicator is actually a mixture of all of these different indicators that changes pH multiple times as you change the pH, changes color multiple times as you change the pH. The end point is what we're looking for in a titration, and the end point is the point at which the indicator changes color, signifying a neutral solution. It's also called the equivalence point. If you actually get the right indicator, your equivalence point is the point where the hydrogen and hydroxide ions exactly equal and is a purely neutral substance. The end point is the point that your indicator changes color, and we call it the end point because that's when our titration stops. So this is the setup for a titration. You have something called a burette, and that's where you put the titrant. You have the analyte in a flask or a beaker below, and this is the process. So you're going to take your titrant, your standard, and place it in the burette. The burette is that tall, skinny thing with a valve on it. You're going to put the analyte, the thing that you're analyzing, is placed in a flask or a beaker below the burette. You're going to add your indicator to your analyte solution, and then your titrant is added slowly, sometimes drop at a time, until the indicator reaches its endpoint. So you just add that titrant, you add the standard in until it reaches the endpoint, and then you are done. So then you can take the volume of your titrant that you started with and the volume of your analyte that you started with, and you can plug all this stuff into the titration equation, and then you can determine the concentration of your analyte. So if we're going to plug it all into the titration equation, we need to know what the titration equation is. Well, it's really simple because it's kind of like a dilution equation because you're kind of diluting but not really. And so basically you have this, MAVA over NA. Well, M is the molarity, V is the volume, and N is the number of moles from your balanced chemical equation. And the A represents the acid, and that's going to equal MBVB over NB. Again, the molarity, volume, and number of moles of your base. So this is the titration equation. Let me show you a demonstration of performing a titration and using this equation, going through and calculating and why and how it's used. All right, so let's see a demonstration of a titration. First off, this is the setup. We have a burette with our standard solution in the burette, and we have a beaker that will contain our solution. I need to actually change beakers because that one had stuff in it already. I have a graduated cylinder for measuring out my analyte, and so we are going to do our titration. So what I have here is a known solution of sodium hydroxide. It's 0.1 molar sodium hydroxide is in my burette. This is my standard solution. I have an unknown concentration of sulfuric acid with universal indicator. That's why it's red. Sulfuric acid is normally clear and colorless, just like the sodium hydroxide. I've added universal indicator to it. Universal indicator is red in an acid, and it is purple in a base, and when you reach that neutral solution, it's going to be kind of a light greenish yellow, so that's the color we're looking for. And so what I'm going to do is I'm going to start off by measuring out 20 milliliters of my unknown, 20 milliliters of my analyte acid. So I'm going to go ahead and measure that out. And yeah, pretty much exactly 20 milliliters. Got lucky that time. So I'm going to put that in my beaker down here at the bottom. Make sure I get all of it in there. So there's my 20 milliliters of acid. I'm actually going to go ahead and record that before I forget. Okay, and I know my concentration of my base is 0.1 molar. So now the way this works is a burette has graduations that start at 0 at the top, and as I add my base to the acid, it's going to drop the level. So once it reaches the end point, marker fell. Once it reaches the end point, I will be able to read my burette to know exactly how much of my standard solution I have added. So I'm going to lower this in a little bit, and I ran this a little bit ahead of time before, so I know about how much I need to add. So I'm just going to let this drain for a second. And so I'm swishing it around a little bit to stir it as it goes. And just keep adding. So I'm going to be a little bit more careful about adding it. I don't know if you can see it on the camera, but it kind of starts to turn a little bit purple and then goes away. We're just going to have it drip, 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 one drop at a time. Still that slightly pink color. Yeah, the pink color is going away. And now changes. There we go. Hopefully you can see now that we now have a slightly yellow color. So I've reached the end point. So I'm going to bring my burette up a little bit so I can read what it says. And we are at 31.21. And that is the concentration of my base that I have, or the volume of the base that I have added to here to get to my endpoint. You'll notice if I go just a little bit past the endpoint, so just a little bit past my endpoint and it turns blue. If I add a lot more, then it'll turn this nice pretty purple color. Basically done with the titration now. But now I just wanted to make it purple because, you know, it's fun. Alright, so now let's do our calculation. Let's look over here at our board to see what other information we need. Alright, so we have our balanced chemical equation. We have sodium hydroxide plus sulfuric acid makes water and sodium sulfate, and we've balanced it. Now the ends here come from our balanced chemical equation. So the number of moles of A is our acid. Well, the acid is sulfuric acid, so the coefficient here is 1. And the number of moles of our base is sodium hydroxide, so that is a 2. And of course, the concentration of our acid is what we're looking for. So what we're going to do is use our titration equation to cross multiply to get MAVA times NB is equal to MBVB times NA, and then we're going to have to find the molarity of our acid. We're going to have to divide by VA and NB on both sides. So that they will cancel out here. So if we plug in our numbers, our MA is going to equal our MB, which is 0.1, times VB, 31.21, times NA, which was 1, divided by our VA of 20.0 times NB, which was 2. So now in our calculator, we multiply that out, and that gives us an answer for our acid of 0.078 molar. And there we go. So now we're going to do another example. In this case, we have 83.8 milliliters of a 3.7 molar H2SO4. So that is the volume of my acid is 83.8 milliliters, and the molarity of my acid is 3.70 molar, is needed to reach the titration endpoint with 50 milliliters of an unknown concentration. So my base is 50.0 milliliters of an unknown concentration of my base of lithium hydroxide. What is the concentration of the base? Now, as you saw in the previous example, we have to have a balanced chemical equation for our neutralization. So we have our neutralization reaction of 2LiOH plus H2SO4 is going to yield, that's an arrow, not an equal, will yield our equation like this. So I just noticed that I accidentally wrote this equation down incorrectly. It doesn't change the way that the rest of the problem is solved, but this should be 2H2 and this is Li2SO4. I don't know why I didn't catch that earlier, but there's the correct chemical equation. But since these are the only coefficients you're actually going to be using, it doesn't change the way the rest of the problem is solved. This, okay? So that means my Na is 1 and my Nb is 2. I get that from my balanced chemical equation. The number of moles of my acid is 1, number of moles of my base is 2. So the equation MAVA over Na is equal to MBVB over NB. And in this case, I'm solving for MB, so I'm going to multiply by NB to get it to cancel out over here. And then I divide by VB, so it'll cancel out here. So my final equation, MB, is MAVA VA times NB divided by VB times NA. So if I plug in my numbers, that gives me 3.70 times 83.8 times 2 divided by 50.0 times 1. And I multiply all that out, and I get an answer of MB is equal to 12.4 molar. So the concentration of my base is 12.4 molar. So this is the process of doing a titration. If these are both 1, if our n's are both 1, then you just take that out of the equation because it just doesn't matter. But you don't have to. But this is the process of doing a titration and the titration calculations. Titrations are very important in chemistry. We use them a lot. They're not always going to be an acid-base titration, but it's still the process of whether you're doing it with acids or bases. The process is basically the same. You're just looking for the point where you cancel things out to figure out that total concentration. So, thanks for watching. Have a day.